Alright, so now we're going to do problem 19. A 12 Newton horizontal force pushes the block that weighs 5 Newton against the vertical wall. So this has 12 Newton and this weighs 5 Newton. And the coefficient of static friction between the wall and the block is 0.6. So mu s is 0.6. And the coefficient of kinetic friction is 0.4. So assume that the block is not moving initially. So the whole thing is balanced. You push the block against the wall with this main tube, and the block itself has its weight, and that's a frictional force that that's keeping it not moving. So let's say. Okay, assume that the block is not moving initially, but after you push this, after you exert this 12 Newton force on this block, will it move? And in unit vector notation, you want to find the force on the block from the wall. Okay, so how do we know that if it's moving or not? When you have something that say you push, this is like the wall and this is the block, and you push it. This comes with the weight, and you push it, and then to see, if this whole thing, this thing will move up or down. So how do we know that, if it's moving? So the thing to be considered is that there's a frictional force between the block and the wall. So we need to know whether the frictional force that experienced by experienced by the block is actually greater than the gravitational its weight, or is less than its weight. If it's greater than its weight, then it's not going to move. It's not going to move. But if it's the frictional force is smaller than its weight, then the whole thing is actually going to move down. Okay. So let's draw a free body diagram just to see how many forces acting on this, so that we can have a better understanding how to analyze the all the force components. You have the rightward force that's pressed against the wall. You have its own weight, and we know that when you have the contact point here, there's always the normal force that's trying to push it up. So if you push this main tube, then you will have another force that's pointing in that direction. So this is the force that's that exerted on the block by the wall, and also there's a frictional force. So that's the frictional force. You have you have this weight of the block. So if if there were no frictional force, this whole thing is actually going to moving downward because of gravity. But because there's a frictional force, so keep it, it can actually keep it to be stationary. So that's the experience of frictional force. So that's a static friction. Okay. So the question is, what is would this weight greater than the maximum static friction? Because the whole thing, in order for this to move, that would be that this weight is greater than the maximum static friction. So we need to find out what is the maximum static friction, and then see if the weight is greater than the maximum static friction. If the weight is greater than the maximum static friction, then of course it will move. If the weight is still less than the maximum static friction, then it will stay there. Okay. So based on this diagram, we can actually calculate the maximum static friction, because the maximum static friction would just be the mu s and then times the normal force. So once we have here is that your mu s is 0.6 and your n is, by looking at this diagram, we know that force and the normal force, they balance each other. So you have the 12. So what is the maximum static friction? You have 7.2 Newton. So this has magnitude of 7.2 Newton, and this has magnitude of 5 Newton. So you can see that the maximum static friction is greater than the weight of the block. So this thing will not move. Okay, so it won't move. That's because the maximum static friction is still greater than the weight. Okay, and then for part B, you're asked to find, what is you're asked to find? You're asked to find the force on the block, by the wall. So we can see that this is the block, and then the force by the wall is this. So you have this. That's this is the force that's exerted on the block by the wall. And also there's this frictional force. That frictional force is exerted from the wall on the block. So what is the force? So we call that force that is exerted on the block by the wall. So this is what we call the FBW, the force on the block by the wall. So In this case, that will be this force and that force. So horizontally, you will have negative 12 I hat, and vertically you have 7.2 J hat. So that will be the force acting on the block due to by the wall. Okay, so just by looking at this diagram, you can see very clearly that this is the force by the wall. All right, so moving on to the next problem. Let's do problem 20. So to draw the diagram. All right, let's see. Let's see. FW. Problem 20. Okay, problem 20. In this diagram, okay, a box of Cheerios. So the mass is given. So the mass of this, let's say Cheerio, that has 1 kilogram. A box of Cheerios and a box of Wheaties, and this one, that's a MW, has 3 kilograms. And they are accelerated across the horizontal surface by a horizontal force applied to a Cheerio box. So you have the force applied this on the left, and the magnitude of the friction force on the Cheerio is 2 Newton. And the magnitude of the friction force on the Wheaties is 4 newtons. And the magnitude of this force is 12 newton. Then what is the magnitude of the force on the Wheaties from the Cheerio box? So in other words, you want to find the force acting on the wheat box from the Cheerio box. So you want to find the FWC. Okay, so let's look at this diagram. So this whole thing is moving rightward, and this one is experience a kinetic friction that's 2 Newton, and this one experience a kinetic friction that's 4 Newton, and there's a rightward force that has a magnitude of 12 Newton, and you're asked to find what is the force acting on this by the Cheerio. So how do we do this problem? We need to draw the free body diagram. Let's look at this wheat box. Okay. On this, just focus on this. We know that there's a gravity, so that's called that WW. Okay, the weight of the Wheaties, and there's a normal force that's pointing upward, so we call that NW. And because the whole thing is moving rightward, so the friction force is leftward. So we have FW, lowercase. Okay, and then there's a rightward motion as well, so that will be the force, and that force would be the force that's that exerted by the Cheerio. So 4 forces acting on this wheaty box. One is normal force, one is a gravitational force, one is a leftward frictional force, and the other one is a force that's coming from the Cheerio. So the whole thing is pushing forward. Okay, so based on this diagram, we can see that you can easily calculate what is the force on the Wheaties by the Cheerio. If we know, because the whole thing is moving and it's moving, and then it actually has acceleration, so we need to figure out what is the acceleration of the system. So what we can do is that if we look at this whole thing as a system, then we use this dot to indicate that the mass, the combined mass of these 2 boxes. So that's your capital M. So your capital M is the mass of the wheat Cheerios and the mass of the Wheaties. So that will be 1 plus 3. That's 4 kilograms. So you have gravitational force, which is the mass of the system. That's your mg. And you have the rightward force. That's your applied force, which is 12 Newton. Okay, and you have the combined frictional force because it's moving rightward. So these two forces, are pointing in the leftward directions. So altogether, you have 2 plus 6, 2 plus 4. So altogether, you have 6. That's your frictional force combined. Okay, and you have your normal force. So in that case, we can see that the normal force and gravitational force, they should balance each other because this whole thing is not moving in the vertical direction. Now, leftward, this is 12 Newton and this is 6 Newton. So we know that the difference between these two will give rise to the acceleration. So let's first find out what is the acceleration of the system. All right, so you have there. So based on this diagram, you can set equation saying that the net force in the horizontal direction is equal to your ma, and your m here is the mass of the system. Okay, so your capital M and then A. So you have the net force, that will be 12 minus 6, and that's equal to 4 kilograms times A. So your A, your acceleration in this case is equal to 1.5 meter per second. Once you know the whole thing is accelerating with that magnitude, then we are ready to apply Newton's law on this diagram. These two forces balance each other. And the net force here between the force on the wedges by the material and the frictional force experienced by the weighted box should give rise to the mass of the weighted box times the acceleration of the system. Okay. So again, how do we set the equation? Well, we say that the net force along the horizontal direction is equal to the mass of the weighted box and then times the acceleration of the system. So this is your net force. Because we apply the Newton's law on this box only, as opposed to this is the diagram that you apply Newton's second law on the system. Okay, so in this case, the net force on horizontally, you have the force by the material, and then minus the frictional force experienced by the weighted box, and that's equal to the mass of the weighted box, which is 3, and then times the acceleration. So now your FWC, which you're asked to find, is equal to FW and then plus 3 times A. Okay? So what is your FW? Your FW is given. That's 4 Newton. And then plus 3 times the acceleration. The acceleration, we calculate that to be 1.5. So that's multiply that by 1.5. So when you do that, the force acting on the weight box will be 8.5 Newton. Okay, so this is the force acting on the weight box by the material box. Okay, so again, so you can see that this really when you apply Newton's second law, your m here, it really depends on which object you're looking at. For this one, it is the total mass of the system. So you add those masses together. Now for this one, you're applying Newton's second law on the weighted box, so you can just use the mass of the weighted box. Okay. And the next one we're going to do is problem 25. Alright, so 25. So let me draw the diagram. So you have this, a block, and it is connected by a rope, and you have another block that's called A, and this is your B, and this is the wall, and this is tied to the theta here. Okay, so this knot is stationary, so it's not moving. So let's look at this diagram. And so you have block B that weighs, so WB, that weighs 711 Newton. And the coefficient of static friction between the block and the table is 0.25. So mu S is 0.25. And angle is 30 degrees. So that's your 30 degrees. Now assume that the core between block B and the knot is horizontal. And find the minimum weight of A for which the system will be stationary. So the whole thing is balanced. This one, if this so you have the weight here. So if this is like heavy, then the whole thing, this B is going to be moving to the rightward direction. Now if this is so it really depends on what is the minimum weight of this A that will keep this whole thing stationary, which means that it's not moving. Remember, there is a frictional force between the block and the floor. So when it's not moving, it means that what is the attempted motion? The attempted motion will be to the right. So in other words, the friction force that the block B is going to experience has to be to the left. Okay, in the opposite directions of the attempted motion. And the other thing is that because you want to find the minimum weight of this A will keep this stationary, which means that this block B is going to experience the maximum static friction before it moves. So let's draw a free body. Whenever you do this kind of problem, draw a free body diagram first. So you have your block B that has a tension. So the tension is just move this a little bit. So you have tension that's in this direction, okay, and you have weight of this block, and there's a normal force here, and then there's a frictional force because the attempted motion is to the right, so the frictional force, the maximum static friction, will be to the left. Okay, so you can see that in order for this to be stationary, the tension in the row has to be balanced by the maximum static friction. Okay, so we can actually just write it down here. That just based on this diagram, that T minus the frictional maximum static friction has to be equal to 0 because the whole thing is assumed to be stationary. And the normal force and the gravitational force, M minus WB, they have to be balanced with each other. And the maximum static friction has to be equal to mu S times the normal force. So we can see that the maximum static friction can be easily calculated because mu S is given, and the normal force is balanced by the weight of the block. So that can also be calculated. And then so the tension. So you can actually calculate the tension. Okay, so this is your tension. So you can calculate tension, but you also find the weight of block B. How is this tension in relation to this block B? So in that case, we have to draw a free body diagram, not on this object, but on this knot. Okay, because if you look at this knot, there are three forces acting on this knot. One is this tension, and one is this another rope, and this is another tension. So how about let's say this is 1, and then you have 1 here. So let me just, and then so you have this. So let's draw a free body diagram. On this, you have tension, always away from the contact point. So you have your T1 here, and then here you have your T2 here, and then you have your T3 there. So you have 3 different ropes, so you have 3 different tension. And this 3 also has to be balanced by the component method. So in that case, we can see that your T1 has to be balanced by the X component of T2. And the Y component of T2 has to be balanced by T3. And your T3, if you draw a free body diagram on block A, so you have the weight of A and the tension T3 that balance each other. So in order to find the weight of block A, you have to find T3. And T3 is balanced by the Y component of T2. So in that case, let's set up equation. Horizontally, your T2 times cosine of 30 minus T1, it has to be equal to 0. So your T1 is equal to T2 cosine 30. Okay, T1 can be calculated because we just went over there's no unknown, so you can calculate this. And then in the vertical you have your T2 sine 30, and then minus T3. The whole thing has to be equal to 0 in the vertical. So which means that your T3 is equal to T2 sine of 30. Okay. So now we are ready to plug in the numbers. So let's say this. How do we find that? So the normal force is WB, and your WB is 711 Newton. Okay. So once we have that, then we can find out the maximum static friction. So maximum static friction is mu S. That's 0.25, and then times 711. So the maximum static friction, we should get 177.75 Newton. And once you have your maximum static friction, based on this, we know that your T1 has a magnitude of this. So that's your T1 magnitude. Okay. So once you have your T1 magnitude, which means that your T1 on the left-hand side, that's 177.75, that's equal to T2 cosine 30. So you can easily calculate your T2, right? Because 177.75 and you have T2 times cosine 30. So your T2, you should get 205.25 Newton. So once you have your T2, then we can plug into this equation to calculate your T3. So your T3 is equal to T2, that's 205.25, and then times sine 30. So then you will have your T3 that has a magnitude of, let's see, you have a magnitude of 102.6 Newton, okay? And that happens to be your WA, because these two have to be balanced each other. So your WA will have is equal to T3, and that's equal to 102.6 newtons. Okay? So that is that. So you can see that, so on this side we have only information, so you can easily calculate T1. On that side you have T3 that's unknown, you have T2 that's unknown, but based on, once you set up equation, knowing that the whole thing is stationary, then all the x components sum up to be 0. All the y components sum up to be 0. Then you can calculate your T3 and T2 just based on the information that we have here. Okay.